Okay, Newton's law of cooling says that the greater the difference in the temperature of an object and the ambient temperature, the surrounding temperature, the faster the rate of cooling. And in fact, it's exponentially faster, as we'll see. We're going to solve this problem. Jim has a problem. He's got to cook up this big pot of soup the night before for the restaurant. He can't put that in the refrigerator. It's just too hot. It's not going to cool enough to be safe. So he's got to get this soup, which has just boiled at 100 degrees Celsius. That's its initial temperature. He's got to get it down to 20 degrees Celsius to feel safe enough to put it in the fridge and let it cool down. So he keeps it running in a sink at 5 degrees Celsius, so that's your ambient temperature. And just with some experimental data, he finds that 10 minutes he can cool it down to 60 degrees Celsius. So we're going to take a look at cooling. The temperature at time t is what we're looking at, what we often want to find. T sub naught is the initial temperature of the soup. In this case, it's 100 degrees Celsius or whatever object we're looking at. And the ambient temperature, the water in the sink, is 5 degrees Celsius. And so if we let the rate of change of the temperature as a function of time be proportional to the temperature of the object at time t, maybe that's 0. And the ambient temperature, the faster, the more rate of change we're going to see, the exponentially faster rate of cooling. Okay, so basically, you can go through this at your own leisure, but we're looking at this equation right here. This is the temperature at time t, whatever we're talking about. It could be the initial temperature, it could be, after 10 minutes, 5 minutes, whatever. This is your ambient temperature. This is the initial temperature of the object, and that's the difference between that and the ambient temperature is going to determine our K. And that's a rate constant, and T is the time. Okay, so the time at temperature, or the temperature at time T, that's the T. Okay, so we have to find out this K for Jim. So we find out, plugging everything in, that the K is actually a negative 0.054. So we have this equation. Now, Jim had done a little bit of experimentation where he put 60 degrees Celsius at T equal 10, okay, and he got this information. So now what he wants to do is to get that soup down to 20 degrees Celsius, and the question is, how much time is that going to take? So plugging in 20 there, we can solve for T, take the natural log of both sides. Go 20 minus 5, you get 15, divide that by 95. So basically you're going to do the natural log of 15 divided by 95. And when you take the natural log of E, that gets rid of it. So you're looking at 0.054 T. So take the natural log of 15 divided by 95. You'll get a negative number. Divide that by negative 0.054. You're going to get a time of like 34 minutes. So just kind of some things to think about here. Law of cooling. The other thing we need to talk about is thermodynamics. And the first law of thermodynamics is that energy is conserved. So whenever heat is added to a system, it transforms to an equal amount of some other type of energy. We're going to be talking about joules. The definition of a system, it's the part we're studying. So for instance, the last video, we had 20 degrees or 20 grams of, or 30 grams of steam, and we took that down to 30 grams of ice at like negative 40 degrees. The system then would be that chunk of steam that got taken through those processes, and the surroundings is. Okay, with thermodynamic properties, we have heat flow, and remember you can find that from our equation times delta T. Work, we are familiar with work. The only thing you might not be familiar with is internal energy. Now these are all going to be in joules. Think about temperature as related to U. They're not the same thing, but as the temp goes up, U is positive. As the temp goes down, U is negative. So if we put an airtight can filled with water on a hot stove and heat it up, not a good idea, because the can has a fixed size, no volume change can take place, no work is done out, work is zero. However, what happens is the internal energy skyrockets, so much so that it could be dangerous. However, what if we could take a piston, put a movable, or take a cylinder, put a movable piston in here, and here's say some steam. Okay, we've had heat flow coming in, we've turned some water to some steam. Now what could that steam do? Well, that steam could push that piston upwards. It could do work on the surroundings. Work, by the way, would be a positive value then because the system is doing work on the surroundings. Now we could compress that piston too. We could have some outside thing pushing down on that, and then work would be negative because the surroundings is doing work on the system. Okay, you can also change the internal energy of a system without adding heat. We don't have to have heat flow in for the temperature to go up. Let's think about this. If we do work on the system, for example, by compressing it, the temperature will rise without an input of heat. Now, keep in mind, we're going to be juggling a few balls here in thermodynamics. Heat can be added or removed, okay? So heat flow could be positive. If I flow heat into the system, I could flow heat out of the system, and then Q would be negative. But if I do it adiabatically, where Q is 0, there is no heat flow, okay, the temperature will rise. And then just again, the sign it. If a system expands around its surroundings, then the internal energy decreases. Again, heat could be added or removed, but without that, the temperature will go down. I've got some examples of taking a look at those. Okay, I think the example must be in the next one. The process of compression or expansion of a gas so that no heat enters or leaves the system is said to be adiabatic. Q is 0. And there's a couple things you can do. You can do it fast. Okay, so there's just no chance for any appreciable heat to flow in or out of the system. And you can insulate. Okay, so as an example here, diesel engines don't, or the trucks don't need spark plugs because you're going to reach what's called the auto ignition temperature simply by compressing the diesel fumes. So you're going to get it hot enough that the diesel fuel can heat. All right, to summarize, if work's done on a gas by compressing it adiabatically, the gas is going to heat up. Work is negative, internal energy is positive. If work is done by the gas by expanding it adiabatically, the gas cools down. Again, Q is 0 because we've either done it fast or we've insulated. Work would be positive, internal energy decreases. Okay, this is the last one I think I'm going to do for this video. If the volume doesn't change, then no work is done. But if there is a volume change, here's some examples of what I was talking about. Blow air from your mouth onto your hand with your mouth open, like forming a large O. The air is warm, of course, we're at 98.6, right? Now blow through puckered lips, like you're blowing on a burn or an owie. Okay, the air feels cool. Well, why? Because you're taking that little blob of air and you're compressing it initially, but then after it gets compressed, it comes out and expands. And as that little blob of air expands, that air is going to cool, and so it feels cool. The Chinook is an example of air that's being compressed and warmed up. And airplanes, you're at an altitude and your temperature outside is like a negative 35 degrees Celsius. So why in the world would we need air conditioners? Because the cabin must be pressurized. And the process of compressing that outside air to sea level pressure cabin for the air to get enough oxygen is that compression, the air would be unbearably warm. Okay, and we're going to talk about this formula in the next video.